Alright, hell yeah. We have a 1-star statics problem. Now the author on this is Paitel Kusalas. Anyway, let's do it. And I don't have any ink in my pen. I have 12 pages of doing this problem. And I'm going to go over it from... I haven't done one of these problems for ages. And so we're going to go over, kind of just talk our way through it. Now, it's still a statics problem. But, oh man, this thing's going to rattle. Anyway, it's still a statics problem, and that means that nothing is technically moving. Alright, this is going to drive me insane. Alright, there we go. Okay, so since nothing is moving, kind of one of the fundamentals that I kind of always go over is take whatever object you have, and I mean, you do a free body diagram, but my way to do it is to kind of like you're cutting it out of whatever. We get that idea. But then when you place it on your page, pretend like it's in outer space. And just pretend like it's the only thing in the universe just floating there. And then just know that you can apply forces to it. So when we have this thing in outer space, kind of like it's basically a square box. That's basically what this shape is. We have two different forces due to these two different masses. Cool. So even just right there, if I put both these forces on this, if this is a statics problem where nothing is moving this way, or rotating, then we have to have we have to have some sort, even if it's just one, we have to have at least one force to be equal and opposite to those. Cool. And so even right here, the first thing that we're given is that we're pushing on this cart with 600 newtons. So if we go to our free body diagram, we have to have something that pushes that way. And the only thing that pushes that way is going to be that point right there. And I guess one thing we need to know about this problem is that if you do have like a point, the force is going to act normal to any surface. But if it's like a point like this and it's a wheel hitting a point, that force is going to act from the point through the center of the wheel. So that's going to be the direction of that force. So yeah, now we can kind of apply a couple things. So if I know that this is going to have what's going to push back is going to be directed at that wheel. It's going to have a component in the horizontal direction and a component in the vertical direction. So the component in this horizontal direction has to equal this 600. And if we have a component of 600 in the horizontal direction, then we for sure have a component in the vertical direction, right there at that point. Okay, so and then the other things that we could have the force under this wheel A and the force under this wheel B holding it. So in the downward direction, we're going to have A, B, and then the vertical component of that, I'm just going to call it N. So that's what I'm going to call this normal force. It's going to have a vertical component and also horizontal. So the horizontal component has to equal P. Yeah, it's just kind of interesting. And this is kind of like my first go at it. I was just like, well, even if I don't know anything going on over here, and then that's a good place to start. I just said, hey, I have two of these forces down. Well, A and B are a pretty good place to like push them up. Now I'm talking like starting from the basics. Even though we're trying to do a tip problem where we did have other constraints, I just kind of want to start off with the basics. I got two forces down, and there are going to be forces under this wheel like going the other direction. So that's kind of the first equation I got. And then this P, something over here has to be equal to P. And then I was just like, oh, it has a component. So it's only going to be, if I know that this angle is some sort of angle, it's only going to be the cosine component. So whatever normal force this is, that normal force is going to be the larger number, but only the cosine component is going to be equal to P. So if I actually solve for N, I would take this percentage and divide it by P. So P divided by a smaller number, that percentage, that means this normal force has to be bigger. So this total vector N, or the total normal force pushing against that wheel, for sure has to be bigger than P, because the horizontal component has to be equal to P. That's that 600 newtons. Alright, so hell yeah. So now we're kind of getting somewhere. Kind of drew some diagrams just to be like, yeah, if this is the force, it's going to act, towards that center of that wheel. And okay, sweet. So that's page 1. Next page, I was just like, well, let's draw these. Let's draw this wheel actually kind of big compared to the car. I mean, the car's just a square. Again, I already said that, but it's just kind of nice to see what's going on here. So I'm going to have this normal force going through the center of the wheel. I'm going to have a force under the wheel. And at this point, I mean, I've already done the problem, but at this point, I didn't realize what the constraints were when things are tipping. I don't think we got there yet. But yeah, right here we get there. And I guess I'll just point it out, is that, yeah, it's so fascinating, especially with tipping problems, when we deal with them in statics, because you're pushing on something to a point where, hey, all of a sudden it might tip over. But up to that very point that you're pushing, it's still a statics problem. You're still applying forces, and other things are resisting that whatever that chunk of mass isn't moving this way, this way, this way, or it's not rotating. Even though like it's about to maybe rotate or tip, at the point before things tip, nothing moves. So that's very fascinating. Even though we have wheels here, and we're pushing on this, you could just imagine that we push on it, but nothing happens at all. But then when you push on it quite a bit, well, a couple things could happen. So I guess let's talk about that. The two things that could happen, and I'm not writing with a pen, else I'll just get carried away. You could imagine that this lip is like hella high, where there ain't no chance this thing's rolling over. Okay, so if that's the case, then when you push on here, well, there's a chance that you just didn't push very hard. Like 600 newtons, but this thing's hella heavy. Cool, you could push all day up against it. It's not going to tip over. So there's an element of like, something could be, have so much mass that you have to, leverage it over, and you just don't have enough force to do that. Cool. But, and you could say, if this lip was like a wall that was this high, like there's just physically no way for that wheel to roll over it. But, let's say that wall is about this high, higher than the wheel. There's still an opportunity for this wheel to lift off the ground and for it to like tip. Cool. So that's a possibility. So that's where, and then from a statics perspective, well, if this wheel lifts off the ground, there ain't no force on it. And then we have to play that game of like, well, right before the thing actually starts to move and tip, it's still a statics problem. We're putting force onto it, like just right up to the point where it's still a chunk of mass that has forces, but no movement. But what happens is this force will go to zero. So there's a split second where this force doesn't have any weight on, this component of B is zero. But we're still holding, but it's still not tipping over. But right at that point, that's going to be the point of tip. And then my bad. I mean, that's still not technically true. That's just the point that it potentially starts to tip. Because, I mean, let's say we do have this wall here. You could put force on this, and you could lift this wheel an inch off the ground, and then just still hold it with a force. It's not tipping over. So there's another aspect of, like, tipping over that if you lift this wheel off the ground by just applying a constant force, still a statics problem. You have a point of contact here, and you have all this weight that's leveraging it down. So this is where we talk about moments. And then you're applying a moment this way. And so those are going to equal. And then they're always going to equal as long as it's a statics problem. As long as there's no movement, this thing can be an inch off the ground, but these weights down and the distance away from those two weights are balancing this this force P, and then whatever whatever distance away it is from maybe these contact points. And this is where, like, man, I did not see this, but if the normal force acts through this point and goes through the center, like if you take your moments from P, they obliterate, you know what I mean, the normal force. There's no moments that the normal force creates if you take your moment about this center of the wheel. And then also the force underneath the wheel doesn't create a moment. So I didn't see that right at the beginning. I probably did it the dumbest way possible, so we're going to go over that. But yeah, you take your moments at A, then everything kind of falls out. And actually, for this problem, you'd want to take your moments at B. We'll talk about that probably at the end. So with this problem, when it comes to like tipping over, basically you would have to apply a force. Oh well, you know, maybe actually no, I probably misspoke, because let's see, the force that's going to be required to lift these wheels off the ground, yeah, that's interesting. I think I am misspeaking, because if I go up to this cart pushed against like a big old lip, and I push on it with a force to get these wheels to leave, there's a chance that as I'm tipping it over, like tipping it over quote unquote, I can back off my force and it's going to be way easier to hold. So actually, this might be true. Like if, I swear I'm not going to write anything, but if I attached, like I always bring in pulleys to the problem. So if I attached a rope to this, and then put it this way, and then I had a pulley here, and then I had a huge weight. So ski lifts will be like this. You know what I mean? They will actually tension their ski lift, you know, the wheel that, you know, where the cables go up to the top and back to the base. That big wheel at the bottom will be on a sliding track, and you'll have cables going around just a pulley, and then it'll be attached to a huge chunk of concrete that's applying that tension. So that's always whenever you're looking at like a constant force, this would be an unchanging force. So the way to get an unchanging force would be to have a rope go across a pulley and then put something heavy, maybe a bucket of concrete, and then because that has mass and it's under the force of gravity, that'll apply a constant force no matter like what the location is. And so yeah, so I guess if in this case, I'm kind of overlooking it. I've not done that part of the problem. But the force required to lift this wheel off the ground would probably put this thing into a position where actually less force is required. You can just imagine if I lift this thing up to here, probably less force is required to actually hold it there from falling backwards. More force would be required to lift it just a couple millimeters off the ground. And so if we're applying that same force to actually lift this wheel, it probably will cause a tip. Yeah, but don't quote me on that. Alright, hell yeah. So this is how I decided to use some kind of tricky geometry. I don't know, I think you'll have to pull this geometry out anyway. I don't want to use angles here. And so I'm going to say that this distance, this hypotenuse, from this point to the center of the wheel, that's the radius. Cool. And then where this hits is 5 millimeters, so I have 5. So, and then I know that this total distance is the radius. So geometry problems always have this. You're like, okay, I know this height, and I know the full radius, but I want to know the other height. Well, all you got to do is go the full radius minus 5. So that's going to be this dimension right there. That's r minus 5. Cool. And then I'm going to take this triangle and put it down here. So we know the radius, we know r minus 5, and if we have a right triangle, my axiom is, hey, if you know 2 things about it, you know everything about this right triangle. And so we definitely know the other side. We use the Pythagorean theorem. which is one side squared plus the other side squared. Square root that is the hypotenuse. But when we have the hypotenuse in one side, we take the hypotenuse squared, and then we subtract this squared. Cool. So this squared becomes r squared minus 10r plus 25. But we're subtracting it. And I think I made a mistake here, because we were going to do r squared minus r squared. So this see how this is r squared minus r squared, but I gotta subtract this entire thing. So a couple pages I do have a typo. This should be plus 10r minus 25, and yeah, so it should be plus 10r minus 25. Hey, I got it right there. I got it wrong there. So yeah, it's kind of interesting. Wrong there, and then I must have corrected it right there. Okay, so what are we trying to do with these dimensions on there? We're trying to get the proportion of this normal component. We want to know its vertical component, and we want to know its horizontal component. And we do that. We know its vertical component is just going to be this dimension, r minus 5, and then you divide it by the hypotenuse. So the hypotenuse is always the larger number, and so the smaller number divided by the larger number is the percentage of this vector in the vertical direction. So that's what we have. So the normal force, the percentage in the vertical direction, is this dimension, r minus 5, divided by the radius. This is going to be this dimension. That's going to be, and I got it wrong, so this is 10r minus 25, should be this, divided by the radius. All right, hell yeah, let's move on. All right, this is pretty cool because, I really like to have my free body diagrams be like less technical, I think is better. So what we have here is a just chunk of mass. We have no wheels on this thing because we don't need them. Even though things, I think it gets confusing with wheels because you're just like, well, can't things roll? And why aren't things rolling? Well, technically, statics problems, nothing's moving anyway. You know what I mean? So we're butted up against something. We're pushing on this. No molecules are actually moving. So we can take the whole thing and just kind of make it into a rigid kind of box with a point that hits A and a point that hits B, and then also a point that hits the curb. So that's where we have the curb right here. The wheel in this picture is bigger than the curb. That makes sense. And I did go over, I don't know if I went over it in the next one. Probably not, but if this wheel's radius is 5 millimeters, well, the normal force is going to be directly that way. So let's talk about that. If the normal force is directly that way, well, it's going to equal 600. Cool. So this one's going to equal 600. And what else? Whoa, I had to think about that one for about a minute. So, yeah, it's kind of fat. It's like, well, if this curb is the same height as the radius, like why? The question would be for me is just like, why can't it roll over that from the equations and then the vectors and the physics? Well, you have a component, horizontal component this way, and you don't have any vertical component, so keep that in mind. So now we will talk about what causes this thing to roll. The second this wheel starts to roll over this, from a statics perspective, is like nothing happened. But the second it wants to roll, this thing will just lift off the ground just a little bit. And the second it does that, hell yeah, you'll probably get roll. And if it lifts off the ground, there is no vertical force at A. So that's the requirement for this, this object to roll, or for this wheel to roll. And if we don't have any vertical component because, this height is the same height as the radius, what does that mean? It means that, if you're trying to analyze roll, this has to be 0. So you just have to take it out of the equation. And so then your weights here and your weights here have to be completely taken up at B. And I guess the simplest way to show that that's just physically not possible is just sum the moments at B, knowing that you can't have any force in this direction. So you have 600, times this distance. And then this is like 1,000, and this is 500. So you have, let's say you have, 600 times this distance. This one's going to be kind of like, this is 600 times 1,200. This is about 1,200 times about 600. And then adding another one, 500 times 375. So the moments here on these two are more than the moment. And am I even saying that right? No, these are all in the positive direction. Oh, no duh. Okay, yeah, I was gonna turn off the camera, but no, I got it. I thought these were actually gonna cancel. No, you have a force here driving, like literally, you are driving this wheel into the ground. If this curb is like that, the moment that you're generating about this is like, hey, this force and is leveraging it down. This force is leveraging it down. And this force P around this point B is just leveraging this whole system. And we know that this whole system isn't rotating. So we have all those torques and leverages from this point B. And so we need something to counteract that. And so the force, the 600 pounds that's pushing up against that, well, that's going right through B. That's not going to do anything. So we must have a huge reaction at A, and that totally goes against this wheel rolling over. So, and I didn't really, if I kind of looked at that, then for sure I would be more in, like the vertical component of this wheel is the most important part. Maybe skip to page 12. So, and if the wheel is super big, and then this little step, this 5 millimeter step is really small, then look, the vertical component becomes pretty large. And so even though it seems that it's at an angle and you're like, oh, I can't tell if the vertical component's large, well, here's kind of the final solution, is the vertical component is 0.9 times, so if this diagonal line is the normal force, this vertical component is 90% of that line, and then this horizontal component's 43%. So one way, it's kind of difficult to actually see the geometry, but let's see if this is the normal direction, and that's going to be whatever force that is. It's 1,380 newtons, who cares? But I just want to know the vertical component and the horizontal component. So what this is a good strategy, is take your hypotenuse and cut it in half, and then see if this horizontal component, the smaller component's about half. And then it's about 50%. It's 0.4, it's 30, it's 43%. That's the proportion of that vector. Cool. And then see if your hypotenuse is about the same size as your larger one, and hell yeah, that you're getting in the range of 90. If you can kind of see a difference, like of 30-degree angles, 60-degree angles, this was 60 degrees, yeah, it'd be 0.866, like 86%. That's 87. You're so close to 90, it's like, basically for smaller angles or really wide angles like this, the longer component is about the same size as your hypotenuse. But this one can definitely vary. This one doesn't go to 0. Hell no. It can still be 40, 50%, even though this one's 90. Okay. So this whole problem hinges on the fact that we have a large reaction force underneath that, and then if we did take our moments about B, we have this, and this driving, the leverage down. But because it's rolling, there is no force underneath A. But we do have the normal force at that at that corner. So it's the vertical component that is balancing out that, and that. And maybe I did do it wrong. You know what I mean? Because I don't think so. I mean, I took my moments about... At one point, I took my moments about here. If A still is 0, I'm going to have this force down and this force down. And then this is going to be positive. But if I take my moments about B, this will be a positive leverage, positive leverage, positive leverage. And then the vertical component... And it's a distance away. It's 1,200 away, so for sure that's going to be helpful. But yeah, so that's yeah. Let's skip to see if I did that. I'm just curious myself if I even did that right. All right, so here's where I do a moment equation about A. I'm kind of curious if I did a moment about B. Because if I sum the moments about B, then you can get the answer pretty easily. All right, I didn't do any errors, but I don't have any good pages on that. So all right, so yeah, so this taking away reaction A is the whole. That hinges on the fact that this thing's going to roll over. If this thing rolls over, it's the vertical component of that point. You know, that's actually providing, we already talked about that. But yeah, there is no reaction at A. Cool. So now we can kind of move on to the next page. Man, and this was brutal. I started summing, yeah, this was just awful. Because I started summing the moments at this point O. I don't know why I chose this, this point right here. Because then, you know, I have all these distances. But then I have to add in this square root 10. You know, if I start at point O and I want to know the leverage of this, I'm going to have to add that distance, which is 700 millimeters. And then I'm going to have to add this. Add those two together and then multiply by this force. And then I'm going to do the same thing for that one. And I'm always going to have to add that distance. So that was just awful. So you can see kind of that process. I mean, it works, but it was so tedious that at a point, this was just the sum of the moments. The second I started summing the forces in the y and the x, I kind of just lost control of the problem and couldn't get a right answer. So, but yeah, if I'm summing the points about that point, it's going to be this weight times this distance from here to A plus that square root, you know, part. Then this is going to be this distance, and that's going to be 825. It's kind of just the, and then plus that square root part. Okay, hell yeah. And that's going to be my negative leverages about point O, if that's that point right there. Then we have a positive leverage. And then this was crazy, because then it wasn't even a nice number either. It's 1,200 plus, yeah, so this was going to be 600 plus the distance was 1,200 plus r minus 5, that little bit right there. And then we also have a reaction at B, and that distance is going to be that 1,200 plus that little remainder. So it's just like, whoa, you know, and let's see how far I get with that. So yeah, I still continue on, but then I was just like, well, if I chose that way, so I was just like, well, let's do it. So then what I did is I said, well, let's just choose, I thought I chose values for things. Oh yeah, so I just said, hey, let's say the radius is 5 millimeters. You know, I wanted to do that scenario. And we sum the moments at O, and what happens when we do that. But I said, I'm going to sum the moments, but the reaction at A is not part of the equation. So I'm going to have the positive reaction at B, the positive reaction at P, and then these two negative reactions. So, and this was just wrong anyway, because I'm going to have a positive reaction at B, which I didn't even include. So, yeah, and it's so fascinating that just by trying to sum the moments in the absolute worst place, it it made me have to redo the problem over and over again. So here was my best attempt at being like, okay, I want to sum the moments right at that point. So again, we're going to have this force, you know what I mean, this 700 plus that little extra, that square root. You know what I mean? So yeah, we got the sum of the moments about O. Some of the forces in the y direction are going to be, and I don't have my little triangle, but this was the vertical component. It was the r minus 5, that little divided by the radius. So that's going to be multiplied by the normal component. It's going to be the vertical component there. We have a b that's also vertical, and then we have the two weights down. So those have to equal each other. Some of the forces in the x, we're going to have this component of the normal force is equal to just 600. So sweet. So we can, you know, I should have started there and then put it into here and then went to this equation. But we can solve for the normal force. It's still in terms of r, but we can put this back into here. And so that's what we do. And we get, you know, just a term with r in it. Now we have, you know, basically this equation that's just a function of r and b. So we have r's and b's. I'm going to solve for b, and then we have, you know, just one thing that's just with r's. So sweet. Go back to my moment equation, and I'm going to put that in there. And for whatever reason, I must have made a mistake. I can go back and see what mistakes I made from this equation. But yeah, I just wasn't able to get the right answer. It's just too complex. Okay, so I still doubled down and tried to take the moments about O. You know what I mean? Just try to do it one more time. And then also, oh no, so even from here, I was just like, well, I still want to take the moments from O, where I chose. Just the worst place I could ever do. But then let's throw in a radius of 15 millimeters. And then so if I did that, what I see is that the forces, you know, the positive leverages are, I can't even read it. So let's just, you know what I mean, I started putting in r is 15, and then where am I summing? Sweet, so finally, you know, I'm summing the moments at point B. I was just like, yeah, that was a total headache. Let's try to find a slightly better place to sum the moments. And hey, this was pretty decent. Still not the best place, but not bad. And so, yeah. But I was still getting the wrong answer, which is really bumming me out. But since this was a better location to sum the moments, let's go over it. I wanted to say, hey, this weight and this weight were going to be positive leverages. There is no leverage at A, this direction. We're going to have a positive leverage also from the 600. So my positive leverages are going to be, did I even do this right? I started with the positive leverage of the 600. And then the distance, and then yeah, and I wanted to be right in line with this normal force. I was just trying to cancel the normal force in the horizontal direction. But yeah, I didn't include those other two forces. So yeah, this is just also wrong. Some of the forces in the y and the x are about the same. Yeah. So when did this problem take a turn for the better? Now here we go. So yeah, sum of the moments at B is going to be g1 times that distance. So that just becomes way easier. I can actually use the numbers on the page. This is 490 and this is 1176. And so we have this weight times that distance, this weight times that distance, and then we have P. You know what I mean? It's 1200 minus 5 plus R. So that's 1195 plus R. Hey, we're not doing too bad. But then in the negative direction, I'm going to have, since I chose my point right in line with this lip, I'm still going to have the vertical component of N. And the vertical component is going to be R divided by 5 divided by R. So that's the vertical component right there. and the distance away, no, that's the percentage. R minus 5 divided by R is the percentage of the normal force. And then so, oh, and I did this first. I said, hey, sum of the forces, yeah, even though this is up top, I did this first. So I summed the forces in the x direction, kind of wised up, and said, hey, this 600 is equal to the horizontal component. So that's going to be this divided by r times the normal force. I can solve for n. So that's going to be, just invert this. So 600r divided by 10r minus 25. So that is the total component of the normal force. But when I'm doing the sum of the moments about B, I just need the vertical component. So I'm going to take this value. That's why we have 600r divided by the square root. And then I'm going to take this. This is the percentage in the vertical direction. Again, using triangles, it's this dimension, r minus 5, divided by the radius. Cool. And that distance away, see, it's still a bummer because it's still 1200 plus this little square root 10r minus 25. So that's going to be equal to 0. I have one equation with one unknowns. And, oh yeah, so finally, I put this into my calculator and finally got a right answer. And I was just like, hell yeah. But I still just used the solver. Like, it wasn't that brilliant. And then I realized, so this is where I had the final aha moment. I was just like, well, I can sum the moments anywhere. And so I started to sum the moments at A. And if I sum the moments at A, I was just like, oh, holy hell. Like, all that normal force goes through A. You know what I mean? Because, and it was, I thought I had to sum the moments right at this point. But since the normal force actually goes through this point and A, if I sum the moments at point A, well, hell yeah. Like, all those just go completely away. And then I only have one force. And if I'm saying that this thing's rolling, the reaction under A goes away. But I'm summing the moments there anyway. But when I do my sum of the forces in the y direction, I don't have a reaction at A. I just have... But let's do this one first. Because if I sum the moments about A, I know everything except reaction B. I know P, and I know, look at this, I know the distance is 1,200. I know these weights. The only thing is you just have to subtract them from 1,200. So this one is 700 away. This one is 825 away. Cool. And so when I'm doing those, from A, I'm saying this one's negative. So so this is negative 490 times the distance of 825 minus this weight is going to be, and I'm multiplying these by 9.8. So the mass times 9.8. That's what I'm using for my numbers, and hell yeah. So we're going to have so this is 120 times 9.8. That's where I get 1,176. So sweet, and it's going to be a negative leverage. And it's a distance of 700 away. Cool. Now we have a positive leverage, 600 times 1,200. Perfect. And then the reaction B is going to be a positive leverage from point A. It's positive. And we have B times 1,200. And I can just solve for B. I didn't realize I could do that. And B was just 423, 422, whatever, newtons. And cool. So once I got that, then I can... what can I do? Oh, this is wild. I was just summing the moments at A because it said be sure to check whether this truck will tip. And B has to have some sort of weight underneath it. If B doesn't have any weight underneath it, yeah, this thing's going to tip, just like we said. If this wheel lifts off the ground and we're applying that force, yeah, I guarantee this thing's going to tip now. But yeah, we do have weight under the wheels. But it wasn't until summing the moments at A, I was just like, whoa, I didn't know I could just solve for B so quick. But I did get, using the solver, I got 50.3 millimeters for the radius of the wheel. And then I kind of go back and kind of draw a diagram using that 50.3 millimeters. Yeah, this was kind of cool because I did want to know the components. We already talked about this. The vertical components, 90% of the normal force, meaning that this wheel is pretty large compared to that lip. This lip is way underneath, and the normal force is almost pushing straight up. And that's necessary to, like, why is that necessary? Is because if we sum the moments at B, that vertical component is a negative, so this, yeah. Oh, and I should go back and do that. Well, no, I thought that was the whole point of summing the moments at B. If we sum the moments, well, this was sum of the moments at A. But no, we got this solution by summing the moments at B. And it's just kind of fascinating that this normal force, like the component in the vertical direction, is 1200. So we have kind of just this number, 1200 times 1200. That's going to be the moment there. And that's equaling the moment of 1200 times 600 plus these two combined. Because their distances aren't very far, you know, it's about, about that. Yeah, that's kind of fascinating. I really want to do that kind of in my calculator. Yeah, let's do that. So we have this vertical component, 1243 times 1200. So that's the number we get right there. It should balance 490 times 375 plus 1176 times 500 plus 600 times 1200. Yeah, and those numbers are the same. So it doesn't seem like it, but whoa, yeah, that's pretty wild. And I think this is pretty much drawn to scale. But that's the only way. If those moments are, if we sum the moments about B using that vertical component, and again, it's because that lip is way underneath that wheel. It has a huge vertical component pushing up. Like when you're pushing this way, that component's pushing up, or while it's trying to climb that wheel, and there is no force underneath the wheel. It's just a vertical component that's pushing up. Well, yeah, there's no force right there, but there's a hell of a force pushing up, which is balancing. Oh, and that's fascinating because it's taking a lot of the weight. Because it's taking a ton of the weight. That's really fascinating. It's making B like only 422. So that's kind of an interesting perspective I'm gaining. Is that when you're pushing this up over the lip, this one has from a statics perspective, you still have the weight of the box and the weight of the cart. You still have to hold that weight vertically, but you're doing so like under A way more than B. And that was the question, is just like, is this force under B getting so small that you're just going to tip it over while trying to leverage it over that point? All right, hell yeah. So about done, and yeah, I just went back and redid it. It's just like, whoa, could I have just summed the moments at I got this answer by summing the moments at B. And I was just like, well, and then I went back to sum the moments at A and realized how simple that was. So then I go back and do that. It was just like, no way. Summing the moments at A gives me reaction B right away, because it's the only reaction, left. If I sum this, the normal force goes away. I know P, I know these weights, and it's just this vertical component B. So my bad on not seeing that. Then I probably should have gone here first. Then sum of the forces in the X, we have this 600, is equal to the vertical component of the normal force. Now we still use that geometry that the normal force and the size of the wheel, this is going to be the radius of the wheel. This little dimension right here is radius minus 5. And then this dimension in the horizontal direction is this. And that's kind of the bread and butter for this problem for me, is to use kind of a Pythagorean's theorem, use that triangle to get the direction of that normal force, whatever the radius is going to be. That's why we don't know what the radius is going to be, so we just don't know what this angle is going to be. But we do know what the components are. So the vertical component is going to be r minus 5 divided by r. We talked about summing the forces in the x. So yes, the sum of the force in the x, the vertical component of the the horizontal component of the normal force is this horizontal distance right here, square root of 10r minus 25 divided by r. And that's going to be the percentage of the normal force in that direction. And that has to equal 600 because you're pushing 600. That's only the horizontal component. So once we get, or we can say we can just solve for the normal force, this is a percentage. So we take 600 and divide it by a smaller number. 600 divided by a percentage between, you're going to get a bigger number. So that's why this normal force is like 1200, because this component in the horizontal direction was only 50. So our triangle is drawn way wrong. This is, at the end of the day, this is what the problem looks like. You have a big wheel, and this wheel has a diameter of 50, and this lip is only 5. Alright, sweet. So, so I'm summing the moments about A, I got B, I come down to sum of the forces, I get the normal force, but the normal force is still, in terms of the radius, I don't know the radius. Now I sum the forces in the y direction. We have that normal force, and we have r minus 5 divided by r. That's the percentage of the normal force in the vertical direction. I know what the normal force is in terms of r, so I'm going to throw that up into there. And booyah, I can, if this is 600r divided by r, I basically just get 600, the r goes away. Still have to multiply by that, so 600 multiplied by r minus 5 divided by the square root 10r minus 25. So that's that term right there. I want to solve for b, so I'm going to say 1600. Oh no, I already know what b is. Yeah, so here's the equation that I finally get to. I have 1600 is equal to 423 plus, and then I have equal to this. So, and I don't think I had to use a solver for this. I might go back and do a technical solution where, I just go, sum the moments about the right location, and now we're just set. We get an equation with r in it, solve for r. And so I throw this into my calculator as a solver. I get this value to the other side, and I say 0 is equal to negative 166. And let's see what I have in here. I don't even think this is the right one. So, hell yeah. So that was just a real easy way to solve for the radius. Okay, and then I go back. Yeah, then I go back, and because I was just so bummed. Actually, yeah, so this is the more technical solution. This is what I started with. I wanted to sum the moments at this point, and I just couldn't figure out why I was messing up, and finally got it. So that's the last thing we're going to do. We're going to sum the moments from this point, and again, that's the crazy way. You have to take this weight. It's a distance of 700. You even have to subtract, 500 from 1200 just to even get that distance. But then you have to add that little extra. Yeah, that's insane. So this weight multiplied by the distance is 700 plus the square root. That's going to be in the negative direction. We're summing the moments about O. So we also have this weight, minus 490, a distance of 825 plus the little extra, the square root. Then we have this distance. That doesn't get any easier because we're summing the moments about O. So we have 1200, but we have minus 5 plus R. So that's going to be 1195 plus R. That's going to be the sum of the moment. That's going to be a positive moment. Cool. Now we need to, what else do we need to do? Oh yeah, we need to, then we need to get the sum of the moment of B. B is a distance of 1200 plus that little extra. And then what is B? Well, we have to go sum the forces in the X. So I guess that's the first thing we did. 600 is equal to this divided by R times the normal force. So take this to the other side, and we got the normal force is 600R divided by that square root. Cool. Sum the forces in the Y, and you say both these weights are 1,666. That's going to be the weight down. That's going to equal the reaction at B and the vertical component over here. I just want to solve for B. And so I'm going to say that's the weight, these two weights down minus the vertical component up. That's going to be B. Cool. Why would I do that? Oh yeah, because I needed B. Yeah, I was trying to finish off the moment. The moment about this point O is that distance to B, but we need to know what that reaction B is. So hell yeah. So that's what we did right there. And I think we need to say that one more time. Sum of the forces in the Y is going to be this, these two forces down. But if we subtract this vertical component, that's going to be the reaction at B. So yeah, this vertical component is going to be R minus 5 divided by R times the normal force. But the normal force we already solved for. So we have R minus 5 divided by R multiplied by this. The R goes away, and we get 600 times R minus 5 divided by the square root 10R minus 25. Cool. So now this is B. We throw it in right there. And yes, I just used the solver on my calculator. But there it is. So we have negative 1,176 times 700 plus that square root part minus 490 times 825 plus the same square root part plus 600 times 1,195 plus R. R X is being used in my calculator for R because we solve for that value of X. And then we have plus 1,666 minus 600 R minus 5 divided by that square root part times 1,200 plus the square root. But I couldn't get this. The first time I tried this, I was making errors. I don't even want to go back and find them. But just the worst place to absolutely take the moment. So it just really shows. But I knew it didn't matter. I knew that even like when I was doing this problem, I was just like, hell yeah, I can take the moments there. And I don't know, it seemed really complex, but it said it was a 1-star problem, and I just went for it. But I must have made some mistakes because hell no, I did not get the answer first try. But there you go. So that's the answer. It crosses at 50. What is it? 50.3. And so I haven't even looked in the back of the book, but this one's in the back of the book, so we can. And hopefully, I just made a huge error, and I did something crazy, because then we can just go back and learn more. But yeah. All right. So we have 50.4. Hell yeah. And I think my answer was like 50.3. And it just depends on what you take for gravity. You know what I mean? So, booyah. We got the right answer. Hell yeah. So I'm pretty excited about this one. And yeah, 50.3 is what I got. 50.4 in the back of the book. Good enough. Alright, so thanks for joining me on this one. And guess what? That's a video.